Well, hello, children. We're moving along at a decent pace. I'm actually pleased with where we're at and the well, not the amount of time that's left in the year, but um, we're in good shape. Some of you may have noticed that some of the assessment has sort of gone by the wayside, and it's not because I've forgotten about it. I really think my duty to you right now is to get you as educated as we can. And so, because we have limited time together, I want to make sure that we see as much in everything of this material to serve you better. So, we're going to just keep trundling along with lessons until I feel that we're done. And that might take us until the end of the year. We shall see. I hope everyone is well. I'm out on my Muskoka room right now. It is glorious and it smells divine because our lilac bush, which is at the side of the house, is in full bloom and it is lovely. So I hope you're well. Today, we are going to start some of the nitty gritty work of 3D vectors. And in particular, we're going to be talking about intersections today. And so intersections occur in different facets. So by the time that we're done this course, we're going to be talking about intersections of lines in R3, intersections of lines and planes in R3, intersections of planes in R3, and distances for all of those things as well. So it gets pretty heavy duty, but we've got this. So right now we're going to start off. I'm just going to say this is intersections. And my house, by the way, is a disaster right now because we're mid kitchen reno, and I've got cupboards out here on the Muskoka room with me, and it's just, I have a huge Muskoka room that's like 16 by 16, and I kind of had to clear myself a little corner on the table here to do my lesson recording on, but we'll get through. Okay, so we're going to talk about intersections, and to begin with, we're going to look at the intersections of two lines in R3. And, intersections, and I'm going to put if they exist, right? Because it's not a foregone that things are necessarily going to intersect. So if you take just two random lines in R3 and I said find the point of intersection, the probability of those lines in fact intersecting is not very high. Like if I asked everybody in the class and Jad didn't have a hand in collusion with everybody to just simply create equation of a random line in R3, frankly the probability of any two of those lines out of the group of 20 plus of you intersecting is pretty low unless you kept it not very creative and you used the anchor point as the origin or something silly like that. However, two lines in R3. So this is what we're going to look at first. So, I'm going to try and combine as many skills as we can just to keep us, thinking all these things. I'm really hopeful that you folks are actually doing some of the homework questions in order to cement these ideas into your noggins, because otherwise it gets away from us pretty easily. So two lines in R3. So here's an example. So I want to find the point of intersection. So we're back to POI being point of intersection instead of point of inflection. Find the point of intersection of the following two lines. And then if it exists, right? Because it's by no means a sure thing. Frankly, if it exists, it's probably because the question was cooked. And if it doesn't exist, it could have been cooked as well, but it could have just been two random ones. So here are the two lines I'm going to give you. And I'm going to give you lines in symmetric form to begin with, just because, it's a good exercise. So we have x plus 5 over 3 equals y minus 2 over 2 equals z plus 7 over 6. So there is the first line, and I'll grab a different color for the second line. And then L2 is going to be, how about just straight up x equals y plus 6 over negative 5 equals z plus 3 over negative 1. So if I simply gave you this question and I said go to it, it would be important for you to recognize, oh, hey, this is in the symmetric form, right? So it's in symmetric form. And frankly, there's not a lot you can do with symmetric form. It's more of a a mathematical exercise of look, ooh, there's symmetric form. It's not used in calculations very prominently. It's worth kind of getting, and sometimes were I in your position, the first thing I would probably do is I would say, oh, this is really x plus or minus 0/1, because that's going to help me, because I'm going to have to go to a different form, right? So this form doesn't help me a lot. Where we actually want to get to is we want to get to parametric form. So I'm telling you that now. So those of you who actually want to engage, pause it and get these lines into parametric form. That's what I'm going to be working on. Okay, so here we go. We're going to keep going. Parametric form. So could I jump right to parametric? Yeah, I probably could. But I would always go from symmetric form into vector form, just because I've got a better idea of what's going on in vector form. So I think that I would convert it to vector form first. So to go to vector form, obviously I'm going to have x, y, and z. Well, yeah, you could definitely jump to parametric form straight, but I'm going to do this as an exercise. So x, y, z is going to be equal to my anchor point. We can spot here. It's going to be -5, 2, and -7, right? So we're going to have -5, 2, and -7. There's my anchor point. And then I need my direction vector, so plus like s times 3, 2, 6, and that is in lowest form integers with a positive leading coefficient. So we're good. So there it is. There's L1. And I'm going to get L2. And again, it's going to be x, y, z. It's humid out here. My hand is not sliding along my tablet as nice as it should. Whatever. So it's going to have an anchor point of 0, -6, and -3. And then I'm going to say plus t times, and the direction vector for this one is 1, -5, -1. Now, I want to point out something here. Some of you might have the instinct of looking at this one right here and say, that's not in lowest form. Yeah, it is, because this is a point, and a point is a physical location. So we cannot reduce a point because that changes its location. If this was over here and it was the direction vector, then yeah, I'd expect you to change that to be 0, 2, 1, right? But do not reduce a point. A point is a location. Direction vector, yeah, it's a vector pointed in a direction. It doesn't matter whether the direction vector, let's pretend that was straight, is that or is this. They both tell you the same thing, right? So direction vectors we reduce, points we do not. Okay, so I'm going to get rid of that just because we don't need those there. But I do want to make sure that we're all on board with that. Okay, back to where we were. So this is obviously in vector form. Okay, and then let's keep going. Let's get it into the parametric form. So I'm going to go and grab this color. I don't know, what color is that? Is that blue still? I don't know. This green? I think that's green. Let's go green. All right, so let's get them into parametric form. So we're going to have L1 is going to be, well, it's x is equal to -5 plus 3s, and y is equal to 2 plus 2s, and z is equal to -7 plus 6s. Okay, there's a little L1, and let's get line 2 now. So line 2 is going to be x is equal to, in theory, you could just say t, but just for kind of symmetry, I like to say plus 1t, 0 plus 1t, and y is equal to -6 minus 5t, and z is equal to -3 minus, and I'm going to actually say 1t, just so I can see, I like to write them all out, even when I don't need that coefficient there. Obviously, I don't need this constant 0 there, but I like to be able to look at it and spot, okay, there's my anchor point, and there's my direction vector. So it's not a necessity. You could have just had x equals t, but I like the elegance of having, at my disposal, anchor point, direction vector, anchor point, direction vector, right? So I like doing that. So it's not a necessity, but I would advocate for that. Okay, so now we've got these ones into parametric form. Now, back in the kindergartens, when we first learned how to find the point of intersection of two lines, no, in grade 9, if we think about grade 9, we always said, oh, I want to know where y1 is equal to y2, because, if we think about two lines in R2, inevitably, if they don't have the same slope, they are going to come to a point of intersection. So that point of intersection is unique in that the first line is in the same place as the second line. So I say, hey, I want to know where is the first line in the same place as the second line. And then we just substitute the equations and away we go. Because it's a sure thing that if they're not parallel, that these two lines are going to intersect in one spot. Down here, we can have lines which aren't parallel, and they don't have to intersect at all, right? Like if you just take two straws and you hold them up in 3 space, and they're not touching one another, they would kind of define where a line would go, and there's a much better chance that they don't intersect than what they do intersect. So point of intersection, if we continue up here, so this is like, y1 equals y2, and we would also find out where is x1 equal to x2. And, when we find that, those ordered pairs are going to tell us exactly where this point of intersection is. Well, that's, the concept is extensible. If I have a point of intersection in 3 space, it means that the first x has to match the second x. And that is an x, I don't want an x there. The first y has to equal the second y, and the third z, that's not the third z, z is third, that's what's got me, but z1 has to equal z2. So for it to be a point of intersection, this must occur, right? To have a POI, this must happen. It's gotta, right? So we can take that and we can say, all right, this is going to be my x1, y1, z1, and this is going to be my x2, y2, z2. And so, all right, I know that x1 has to equal x2. So that means that this chunk here must equal this chunk here. All right, well, here we go. So we're going to have -5 is equal to 3, not equal to, excuse me, -5 plus 3s is equal to 0 plus 1t, right? And then I want to do some rearranging here. So I'm gonna rearrange this, clean this up a little bit. So I'm gonna, how about we do this? So I'm gonna say this, I can simplify this to be 3s minus, and I'm not gonna keep the coefficient anymore because we know we're gone into equation form, is equal to 0 plus 5 is 5. So there's an equation. This is the equation that I got from my x's, right? So there's an equation that I got from my x's. Then I'm going to look at my y's, and my y's say, all right, well, it's going to be 2 plus 2s is equal to -6 minus 5t. All right, I'm going to do a similar rearranging. So we're going to have that 2s plus 5t is equal to -8. Okay, -8. And so this is the equation that came about from my y's. And then I'm going to do the same thing for my z's. So we're going to have -7 plus 6s is equal to -3 minus 1t, or just t, I guess. And I'm going to rearrange. So we're going to have that 6s plus t is equal to 4. And this equation was brought to you by the letter Z. So what we have here, we've got 1 equation, 2 equations, 3 equations, but we've only got 2 unknowns. So we know, hopefully from back in grade 10, that if we have 2 equations, well, if we have 2 unknowns, we only need 2 equations to solve. So we have a bit of a conundrum here. We have 3 equations, but only 2 unknowns. So here's our strategy. Okay, our strategy is going to be, after we have these equations set up, we are going to choose 2 equations and solve, and I'm just going to say and solve, right? Because if I said S and T, that's going to necessitate that you always use S and T. And those are just parameters. They could be any variables you want as long as they're consistent, right? Because, has to be the same S for all these guys. And I suppose I really should have said S a member of the reals. And up here, this could have been, this could just easily have been M, but it doesn't matter. So we have T, a member of the reals. So you choose two equations and solve. And I don't care how you solve them. You can either solve them with substitution or elimination, and choose whichever two you want. And I would always, advocate that you choose the two that would, expedite the most your solution. And so I look at this and I've got like a minus t. I look at this and I've got a plus t. And I think, oh, I can do elimination method on those things, and it just falls away darn near instantly, right? So I'm going to choose equation 1, and I'm just going to rewrite it. So we got 3s minus t equals 5, and I got equation 2 here. And equation 2 says that this is 6s plus t is equal to 4. And sorry, that's not equation 2. I'm a bonehead. Equation 3. And then I'm going to add, because if I add, it's going to get rid of the t. So I'm going to have then that 9s equals 9. Divide both sides by 9, divide by 9, and we're going to get that s equals 1. Huzzah! I have a value for my s. But there are two variables, so I need to substitute back in to get the t. Here's where students often go wrong. These are the two equations that I began with. Those are the two equations that I must finish with. Please don't take this s equals 1 and walk back here and say, huzzah, I'm going to put it in here and solve for my t. No, no, no. Equation 2 is not playing right now. I'm playing with equation 1 and equation 3. So I must continue until I have a solution using those two equations. So I'm going to take s equals 1, and I'm going to put it into this one right here. So we're going to get 6 times 1 plus t is equal to 4. 6 times 1 is 6. Move it over. And we're going to find out that t equals negative 2. So I now have that t equals negative 2. So this, I contend that I have a solution now that s equals 1 and t equals negative 2. And I could go ahead and I could check it in these two things to make sure that it was right? So if s is 1, that's 3 times 1 is 3, and then minus negative 2 is 5, so that's going to be 5. So yeah, that one works out. That's nicely. And then 6 times 1 is 6, and then minus 2 is 4, so forth. Yeah, so this is absolutely a solution to these two equations. Now, realistically, as long as these two are linearly independent, so like they're not, scalar multiples of each other, so as long as it's not like 3s, 6s, negative t, negative 2t, they're going to have a solution, essentially by saying as long as they are not, the same line, we're good to go. And we are. So there's s and there's t. Here's why it's important. We're always going to get a solution to s and t from two equations. Okay, whether these two lines, and by the two lines I mean these two original lines, intersect or not, we will always get a solution here. So we have our solution. Yay us, huzzah. There is our solution to the two equations. Yay. But what we need to do now is we now must check in the unused, oh, that looks like used. Let's clean that up a little bit. So that's terrible. I'm looking like a toddler on crack. So check in the unused equation your values, and I'm going to say s and t here, because you know what I mean. So if you used m and n, whatever, that's what we would be using. So we're going to have to check in our unused equation. So my unused equation was equation 2. And so I'm going to do a formal check, as are you, because you are responsible, diligent children. So I'm going to be checking that 2s plus 5t is equal to negative 8, where s equals 1 and t equals negative 2. Now, I wrote that again so that I can read it when I'm down here. You don't have to rewrite all of that, but you really should say check and then what you're checking. So formal check here, I'm going to say that left side is equal to 2s plus 5t, and that the right side is equal to negative 8. And then I'm going to substitute in and just validate that, in fact, these equations hold. So 2 times 1 plus 5 times negative 2. 2 times 1, Jad, you don't need your calculator, it's 2. minus 10 is equal to negative 8. So I have found that left side equals right side. So because we found that, and you can celebrate, you can give us a woot if you really want, right? Because not only did S and T work for the first two equations that we used, it worked in the third one as well. This right here, this indicates the lines do intersect. Okay? Had we taken our S of 1 and T of negative 2 and it came out to be like 5 and negative 8, what that would indicate to us then is that in fact those two lines do not intersect. But we're not done yet. We know now that they intersect. What we need to find out now, of course, is, well, where do they intersect, right? I wish I was able to cut and paste that. So we got x equals negative 5 plus 3s. I should have done this in Smart Notebook. X equals negative 5 plus 3s. And then we're going to have that y equals, I believe it was 2 plus 2t. 2 plus 2t. Let's go and check. 2 plus, or 2s. Dang it, I'm a bonehead. Let's clean that up again. 2s. And then z is equal to negative 7 plus 6s. Okay, so you could have gone back and retrieved either equation. We could have retrieved the first equation or the second equation. It doesn't really matter. We can take either one. But we should know now that I can take an s value of 1 and substitute it in and get our ordered pairs. So it's going to be negative 5 plus, well, my s value is 1, so plus 3 times 1, and that's equal to 2 plus 2 times 1, and that's equal to negative 7 plus 6 times 1, right? And so that means that my ordered pair is going to be x, or my ordered triple, excuse me, x, y, z is equal to, I guess that's going to negative 2 plus 4 and negative 1. Okay, so I contend that this is our point of intersection. And if I wanted to check it, which is not a bad idea, but on a test situation, I wouldn't take the time to do this. This would be a comeback to do it. Check it. We can choose the other equation, the other original equation. And so I'm going to get the parametric form of that. So we had that, x was equal to 0 plus 1t, and we have that y is equal to negative 6 minus 5t, and we had that z is equal to negative 3 minus 1t. That's 0, 1, negative 6, negative 5. 0, 1, negative 6, negative 5, negative 3, negative 1. Yep, so that's good. So now we can substitute in our t value, and we said that our t value was negative 2. So 0 plus 1 times negative 2, and is equal to negative 6 minus 5 times negative 2. And we have that negative 3 minus 1 times negative 2. And so that means that this x, y, z is equal to negative 2, and that's going to be positive 10. Negative 6 plus 10 is 4. Lovely. And that's going to be positive and negative 1. And again, we can celebrate with a hearty huzzah because, of course, those 2 points are the same. Okay, so strategizing here, what we would do, in the grand scheme, get them into parametric form if they're not already in parametric form. If they are, don't do something silly like change them and bring them back. Get them into parametric form. Choose any two of the parametric equations. And again, be conscientious about that. Choose the ones that are going to make your life easiest. Solve those two parametric equations for the parameters. And then take those parameters, substitute them into the third parametric equation. Make sure that it holds. If it does hold, then you can take that parameter and put it back into your original equations and find your point of intersection. If you have time, you can validate that in fact you have done that correctly by, checking in your other equation, your other original equation. So that is how we find out whether in fact a pair of lines in R3 intersect. Okay, so there is our strategy. So I would suggest, I'm not going to do it because I don't have a lot of room here and I don't want to take more of my instructional time than I need, but I would suggest that you recap, you rewind that video, just the last couple minutes there, where we outlined that, and you create yourself a little cookbook recipe of how it is that you find out that two lines in R3 intersect or not. Okay. All right. So next type of intersection that we're going to talk about. And how much room is it going to? Yeah, I can write small. I can't write small, but I'll do my best. Intersection of a line and a plane. Ooh. Intersection of a line and a plane. Now, I am not going to contend that what I'm showing you in any one of these is necessarily the only way of solving something. Okay. What I am showing you is typically what would be considered the most efficient or most intuitive, most understandable way of solving something. And that is going to always be my way forward. If you think, hey, I'm able to solve this a different way, and you're concerned maybe your way makes sense to you, shoot me a picture or a question or something with the method that you are using, and I will give you a yay or a nay. Sometimes something works, but is not extensible, meaning it works for certain circumstances, but it will not always work. But there are definitely multiple ways that are extensible for finding some of these solutions. Okay, so let's look at this one. So we'll start out with another easy one here. Let's go with an easier case. So if I want to say, find the POI if it exists of the following two things, a line and a plane. So I'm going to say that L1, so the line, I'm going to give it to you in parametric form. So we have x equals 4 minus 1t, and we have y equals 6 plus 2t, and z is equal to negative 2 plus 1t. Now, I want to take a minute and do a segue here, or like a little aside, and say, you guys know my handwriting is lackluster at best. However, generally speaking, I can tell my characters apart. Once you get into three space vectors, we're tossing z's, we're tossing parameters, we're doing all kinds of things. It is really, really important that your characters are written in such a way that you can tell the difference between them. Some of you, that's not going to be an issue. For others out there who have the toddler on crack handwriting, it is time to be very diligent in our character writing such that we can tell these things apart. Notice that my Z's always have a cross through them so that I do not mistake them with my 2s. My 7s have a cross through them, right? It's important that you choose a character set that is unequivocal, like I can't think of the right word because I'm old and busted. That is without question, you can tell what character it is that you have written time and again. Some of you write 4s that look too much like 9s and stuff like that. It is really time to mature your character writing such that you will always be able to tell them apart. And I can't tell you how many marks students in this class have lost simply because they can't read their own writing. And it is never more prominent than when we get into three space vectors. Okay, so here we go. So there is the equation of the line. And then I'm going to say the equation of my plane. So a plane equation I'm going to give you is 2x minus y plus 6z plus 10 equals 0. So over here, we've got, this is, of course, parametric form. And over here, this is, of course, Cartesian form. Now, this is the ideal. So if we are considering whether a line intersects with a plane and a line is given to you in a form that is not parametric form, first thing you're going to do is convert it to parametric form. Similarly, if I give you the equation of a plane and it is not in Cartesian form, the first thing that you're going to do is convert it into Cartesian form. Okay, so if we kind of think about what this looks like, it means that we've got this plane out here somewhere, and then we got a random line that's impacting and going through the plane, and we are looking for this spot right here. This is our point of intersection. Okay, that's what we're after. Now, we have one parameter. This t must be consistent for this whole shooting match. And we know that every point that lays on this plane must satisfy the equation of the plane. So when I take my ordered triple, if I substitute the x, the y, the z in here, it's got to be that when I simplify this entire left side, it percolates down and becomes a 0. Well, we can make use of that by saying, well, here's my x value, here's my y value, here's my z value, and I only have one variable that represents all of those things. Let's make sure that the variable that I put in there is the one that in fact makes the left side and the right side of this equation work. So what I'm going to do is I'm going to take and I'm going to substitute the x, the y, and the z components of those parametric equations into my Cartesian equation. So it's going to look like 2. I'm going to replace this x with this x, right? This to this. And so we're going to have 4 minus, and it can just be t now, minus y. Well, my y is 6 plus 2t. And then my z, so plus 6 times negative 2 plus t plus 10 equals 0. So we've got a big equation, but really I could just as easily have given you something like this in grade 9 and said solve for t, and that's all we're going to do. So we're going to expand, we're going to distribute, so we're going to have 8 minus 2t minus 6 minus 2t plus, minus 12 plus 6t plus 10 is equal to 0. And so we're going to gather my like terms. Negative 2t is negative 4t, plus 6t is 2t. So we're going to have 2t, and then 8 minus 6 is 2, minus, minus 12. I've lost track. 2 minus 12 is negative 10. Negative 10 plus 10 is 0. So 2t, in theory, I can say plus 0 equals 0, and then I'm going to say, all right, well, the zeros are gone. I'm going to divide both sides by 2, divide by 2, and we find out that, in fact, t is equal to 0. Now, this step right here, okay, I'm going to come back to this in a moment. This step right here is a special one, and this is noteworthy, and we're going to talk about it more in a second. But what we found is well, 0 is a number. Like, it's a real number. It's actually a natural number. It's not a natural number. It's a whole number. It's an integer. It's lovely. And so t is the special value of t of 0 is the special value that I'm going to put in here. So that means actually, in fact, that if I put the 0 in, I mean, I can, be really ridiculously explicit about it. X equals 4 minus 1 times 0, and y equals 6 plus 2 times 0, and z equals negative 2 plus 1 times 0, and then simplify. So we're going to get that x, y, z is equal to 4, 6, negative 2, and what we have right here is this, folks, is our point of intersection. Right there. There is our point of intersection. Okay. Oh, where's my cat? I was wondering what's going on. Okay. So yeah, there we go. That's a point of intersection. And you could validate that. We know for sure that it lays on the line. There it is right there. It's the anchor point of the line. Not very adventurous. And you could put these values all in, right? Put the x value, put the y value, put the z value, and confirm that when you simplify this, it equals 0. And if it does, means that that point is on the plane. So 2 times 4 is 8, minus 6 is 2, plus negative 12 is negative 10. Negative 10 plus 10 is 0. 0 equals 0. Woot, it's on the plane. So we found that, in fact, the line and the plane intersect at this point right here, right? So we are happy about that. Now, back to our noteworthy line, okay? There are a number of different cases that can occur on this line, and they all denote different things, and it's important. So moving forward for the rest of this course, frankly, um, kind of the second last line in a solution is going to be very, very telling. It is going to dictate various scenarios. So let's think about the different scenarios. I'm almost in a room here, but that's okay. There are different scenarios that can occur when we have a line and a plane. So think about the different scenarios that can occur when we have a line and a plane. So case one, which is what we just had right here. And I'm going to do little diagrams, even though they're poor diagrams, but they're diagrams nevertheless. We can have a line, it comes along, it intersects, and it goes through the point. There is our point of intersection, right? POI. Yay, team. Anytime that we are going to have a point of intersection, this line right here is always going to be a non-zero t. So why did I write a zero? Okay. So we're going to have a times t equals any number, and a cannot equal 0. Okay, so it could look like 3t equals 5, 2t equals 17, 4t equals pi. Any of those fall into the case where a does not, well, I've already got it there. A doesn't equal 0, right? So a is a member of the reals. A is a member of the reals such that a does not equal 0, right? And as long as that's true, we in fact have one point of intersection, right? And that's, I don't have a highlighter, but let's pretend there's my highlight. That's not really very nice yellow, but I thought it was yellow. Is that not yellow? Is that yellow? Is that yellow? Maybe that's yellow. Whatever. Right. So when we have this satisfied, right? If it looks like this, it guarantees that we have one point of intersection. So it means there is some t value that we can put into our line that will take us from our anchor point out to wherever this spot is, right? That's what that's saying. We're finding out how many direction vectors we need to move along our line from our anchor point to get to the point of intersection. So that's one case. Let's look at a second case. And so think about it. How else could a line and a plane intersect? Well, case two. Ooh, I like that color. What color is that? Is that blue? Is that purple? I don't know, but I like it. Um, we've got our plane and our line. And our line is parallel to our plane. Okay. So the line is parallel to the plane, but not on the plane. So in that case, it means that there is not going to be any points of intersection. So they never, I really like this color, never intersect. It's got to be blurple or something. I don't know. I like it. So what we would get on this step right here for this one, we would end up with, there is no value of t, right? So if we think about, a line in R3 looks like, x, y, z is equal to P naught, our anchor point, plus N or T or whatever you want, T times our direction vector, right? And in this case, there is no number of times I can follow my direction vector from my P naught to get down to there. So there's not a valid T that ever exists. So this equation, this step is going to look like 0T equals a number where that number may not equal 0. So cases like this, it could be 0t equals 4, 0t equals -7, 0t equals 13.2, that's not a 2, 13.4, right? Any one of those, if you tried to solve for t, t would not be a member of the reals. Okay, Brianna, shush, chatty monkey. Okay, so 0t equals any number that's not 0 means they never intersect. There is no value of t which can make this true, right? So if you spot 0t equals a non-zero number, what it means is they are parallel. Now, how could you check that? Well, one way you could check it, you think about it for a second. How could you check it? Well, this plane, when we think about the Cartesian equation of this plane, the Cartesian equation uses the normal, right? And what would have to be true about the normal vector and this line? Well, if this line is parallel to this plane, it must mean that it is perpendicular to the normal vector. So what you could do is you could take, this is as far as I would go, but it's one of those things, if I had the time, you could do a check and you could validate that the normal vector dotted with the direction vector equals 0. Okay, the normal vector dotted with the direction vector is equal to 0. What that means is that the line and the plane are parallel. Okay, so there is the second case, case 2. Case 3, maybe I kind of gave it away just with what I was talking about there. Case 3, we'll go here. So case 3 is going to be a plane, and the line is going to be on the plane. Okay, so the line is on the plane, which means it's parallel as well, right? It's parallel to the plane because it's on the plane. So this one is parallel, not on, and this is just, they're not parallel. They intersect, okay? So intersect if they're not parallel. If they're parallel, not on, they never intersect. Line is on the plane. It means that how many different points are there of intersection? An infinite number, right? And so this equation is going to end up looking like 0t equals 0. And why does that make sense? You're like, well, you can't divide by 0, right? Like I can't go ahead and go, oh, divide by 0, divide by 0. Like that'll break. That's bad, right? So we don't want to do that. But if we think about it, it doesn't matter what value of t you put in here, it will always be true because 0 times anything is 0. So this means that there are an infinite number of solutions. The line is on the plane. Okay, how cool is that, right? So this sort of second last step is going to dictate to you which of these 3 cases we in fact have. Okay, so it's got to be case 1 is they're not parallel, they're going to intersect. Case 2 is they are parallel, but not on the plane, so they never intersect. There's no solutions. I guess I should have said that. No solutions. And then the third case is the line is immediately on the plane. And in that case, there's an infinite number of solutions, right? So if it said, find a point where they intersect, take the anchor point of the line, or take and put whatever t value you want into your line, and it will tell you another point that's on the plane. Every point that's on the plane, or every point that's, excuse me, I have to be careful. Every point that's on the line is also on the plane because the line is on the plane. Okay, so we've got one more, and I don't have room to do it, so I'm going to save this. File, save as, and I'm going to save it as a JPEG again. JPEG, and this is MCV, and this is MCV4U vectors and intersections. Oh, yep, that's good. And then, file, save as. No, I did that. Cancel. File new. And I got a new one. It always starts right in the middle, which is weird. I don't want to start in the middle. I'll start at the top. Okay, and the last type of intersection that we're going to talk about right now is going to be, and it's what time is it? I have no idea how long this video is. I'm gonna plug through. This is important, and depending on how long this is, I'll kind of dictate how much more stuff we're going to do this week in my other lessons. Okay, so this one is going to be, so we've done the intersection of 2 lines, and then we did the intersection of a line and a plane. Those of you who are speculating children, this is going to be the intersection, oh, hello, Diesel, of 2 planes. in R3. Now, this may be better, instead of saying intersection, we could say interaction, right? So, because it's not a sure thing that two planes intersect. So, in the same way that we considered three cases for a line and a plane, I'd like you to think about the different cases that can occur between two planes. Okay, so if we think about them, case one. Case one will be the ideal case where what we have is we have two planes, and grab a different color here. And then it comes out this side, and I'll even clean that up a little bit. Let's get my art eraser. Okay, so there we go. What we have now is we have two planes. So this is pi 1, this will be pi 2. So how did they well, two planes can intersect in a line. So two non-parallel intersecting in a line, right? So when two planes intersect, they can intersect in a line. And so this right here, let's grab another color. This right here would be the line. Oh, that's a terrible arrow. Nevertheless, an arrow. This is the line of intersection. Ooh, a line of intersection. I like that. Line of intersection. Okay, lovely. Let's go case two. Case two. So case two is less interesting. We have a plane and another plane. And so what we have is two parallel, non-coincident planes. That means there are two parallel planes that do not touch. Okay, so this has a line of intersection. This, of course, has no intersection. Okay, so no intersection. And then case three, can you guess what case three is? I bet you probably can. Case, that's not a different color. Case three is going to be, we have a plane, and let's get this color, sure, whatever color that is. Another plane. And even though I'm drawing it smaller, in reality, they go forever because they're planes. And what we have is, this time we have two parallel coincident planes. Planes. Wow, that's terrible. Planes. So coincidence is just a fancy word for in the same place, okay, in this context. So two parallel coincident planes. And what it really means, it's the same plane, okay? And so that means there are an infinite number of solutions. It is the entire plane. Now, infinite number of solutions isn't unique because a line of intersection is also an infinite number of solutions. But when they are parallel and coincident, it means that in fact they're the same friggin' thing. So any point that exists on one plane exists on the other. Whereas this, there is only a special line of an infinite number of points. Okay, so those are the three cases. The question becomes, how do we identify the cases? Now, you might say, well, wouldn't it be obvious? Wouldn't this case be obvious? And the answer is sort of, right? It depends on what form I give you the equation of, right? So envision for this one, or let's go over on this one because they're in different places. If I gave this to you in vector form, so let's remember what vector form looks like. So just as an aside, we've got vector form of a plane, vector form. Okay, so that's going to be, plane one is, x, y, z is equal to p naught, so my anchor point, plus uh, s times direction vector 1 plus t times direction vector 2. Okay, so that's the vector form of a plane. Now, these two planes are parallel, but it doesn't necessarily mean they have to have the same direction vectors. So imagine that, you had one direction vector on this plane, if you were looking directly down on it, that went, the direction vector was at 12 o'clock. And this had a direction vector that was at 3 o'clock. Okay, you can imagine those are my two direction vectors, and there's my anchor point. Where this one down here, what color is that? Don't know. Maybe it has one that goes at 10:30 and one that goes at 1:30. And there's my anchor point there, right? And so you can't simply look at the direction vectors and tell. It's not obvious at all. So if I give it to you in the vector form, you cannot at a glance at all tell what one of these cases are. And you might say, oh, well, maybe the anchor point's not the same. That doesn't matter. This one, like this one over here, where it's entirely the same plane, you can have one anchor point there, and for the other plane, the anchor point's over here. So you can't tell by the anchor point. And same deal here. We could have a direction vector like this and this, whereas this one had a direction vector like this and like this, right? So in vector form, there is absolutely no way to tell whether in fact these planes are parallel or not. You just can't. Okay. However, if it is in Cartesian form, we have ax plus by plus cz plus d equals 0. Okay. Now, recall, hopefully you remember, the normal vector is on display. The normal vector is a, b, and c. Now, if we hold true to our, instruction of our normal vector needs to be in with a leading positive integer and in lowest terms integers for the rest of it, that would mean that the normal vector for this one and the normal vector for this one are identical. Okay? If the normal vectors are identical, then that means that they are parallel. Okay, so in this case, normal vector 1 would actually equal normal vector 2, guaranteed. Same as over here. Well, obviously, it's the same plane, right? So this one would have normal vector 1 is equal to normal vector 2 as well, right? So if it was in Cartesian form, this would be a trivial thing to solve, okay? You would know whether they were parallel or not. Now, how would we tell whether it was case 2 or case 3? Well, case 3 is absolutely the same equation, right? So the only way I could come up with a case 3 that wasn't like a ridiculous dead giveaway. So imagine that I said plane 1 is going to be 2x minus 3y plus 5z plus 12 equals 0. Okay, there's plane 1. Plane 2. If it is this case, imagine that I said, oh, I'm going to really mix it up. Negative 4x. You can tell me what the rest of this equation would be, right? It would then be plus 6y minus 10z minus 24 equals 0. They must be, I don't really have room, full scalar multiples. Okay, that's because they're the same plane, right? So the only way that they're literally not the exact same equation is if I'm not really following the standard of having the normal vector in reduced terms. We, by all accounts, should divide through by -2 to get that to be a positive coefficient and have it be in lowest terms. And then they would be the exact same equation. Okay, so the normal vectors match, easy peasy, easy peasy. What would this one look like? Well, imagine that we said plane 1, and the normal vectors have to be the same again. So, if I said 2x plus 5y plus 6z plus 10 equals 0. Well, if we followed the reduction as we're appropriately supposed to, 2x plus 5y plus 6z. So there's our normal vectors matching, meaning they are parallel. The only way they can be a different plane is if the d value is anything other than 10. So plus 1 equals 0. So we can inspect the d values. So we have a different d value, but over here we have the same normal. Okay, so different d values, same normal. Over here, if I do my proper reductions, we have identical equations after being reduced. And over here, what we would have is, I could write plane 1, and I'm gonna actually cook a couple here. So, plane 1 is going to be x minus 2y plus 3z minus 6 equals 0. And then plane 2 is going to be, well, as long as the normal vector is not identical, right? If you think about any two planes, if you took two infinitely large sheets of Bristol board and they weren't perfectly parallel, sooner or later they are going to touch. And how would they touch? They would touch in a perfect line. Okay, so here's my second one: 2x plus y plus z minus 7 equals 0. So, as soon as we can spot that the normals don't match, therefore, if the normals don't match, what it means is, of course, what does it mean? If the normals don't match, it means they intersect in a line. Now, I have a feeling that this video is enormously long as it is. So what I'm going to do is I'm not going to solve this one right yet. I'm going to do that in my next video because I have a feeling that this is already really long. So thanks, folks, and tune in again tomorrow. I think what I'm going to do is I'm going to record a second video right away. I mean, I always record them right away, but I'm going to post both of them on the same day and then not post on the Tuesday. Okay? Thanks, guys.